Hello, it's Keith here, and this is the 6th of the YQuest series and 68,000 tutorials. We're looking at the NeoGeo version of the game today. This is the NeoGeo port. You can see it here. Now, the graphics here are using the fixed layer, which is really designed for text. So we're kind of cheating a bit here, and the reason I'm doing that is this is based on the simple series, and the fixed layer is very easy if you're a beginner to do graphics. What we're going to do later on in a later lesson though is we're going to add hardware sprites to this, so we'll have some proper nice smooth movement. Point I'm making is that even though it's a bit basic at this stage, it's not too hard to extend it and make the graphics better later on once we've got a game to start from. Anyway, that's the game we're looking at. Let's go over to the source code and let's see how the game works. Okay, so of course you can download the source code from my website. We're going to go over it now. Now, this is the platform specific NeoGeo code. The first thing we've got here is we're having to limit the screen size and the collisions. Now, the different systems have different screen sizes, so the boundaries are defined differently on each one. And also, because this system is tile-based, we can't show with the proper definition the enemies and the player and things. So we're reducing the collision detection accuracy so that the collision detection logic matches the displayed sprites or tiles, as it were, because it's using the fixed layer tiles. So that's what's going on there. We're defining some memory for the game code here, and then we've got the massive header here. This is all very generic. As you say, I got this from a website here. This website has some fantastic headers, and I couldn't have done it without them. So that's what we're using here. The actual start of the game code itself is here. This is the start of today's code. So first we're kicking the watchdog. This, if you don't know, this is the crash protection of the NeoGeo, being as it's arcade hardware. If the system stopped responding by kicking the watchdog would reset the machine. So we don't want that to happen. So we have to do that regularly. We're then defining the colors here. They're defining the background color, and then we're loading the rest of the colors in from a defined palette in native format. So we're starting from this memory address here, and we're defining 16 colors. And then what we're doing here is we're just initializing the fixed layer and the sprites just to clear everything off. Now, I mentioned that RAM before. This is where all of the variables for the game, the position of enemies and objects and the score and things all reside, because this is of course all ROM. So we're just clearing that with this CLDR command, which just clears banks of memory here. And then we're going to start a new game. So we're setting up the number of lives, clearing the scores, zeroing the level, resetting the player object and silencing the sound. Then what we do is we draw the fantastic title screen. Some sarcasm there, it's not entirely fantastic, but it's at least okay. I think I'll give it okay. So yeah, the title screen, which you can eventually see starting up here. Where is it? There we go, this thing. This is a tile map, it's called Title Pick, and each part of that, go away, is 1 byte, so there's 1 byte per tile. So we load in each tile. If the tile's non-zero, we're going to show it to the screen. So we calculate the position within the fixed memory of that tile, and then we show the tile using these routines. We'll see those in a moment. Now we repeat until the entire title screen has been shown, and then we're showing some messages here. Now the font is also in using the fixed layer. We'll see that as well later on. Here's the start of the level code. Every level starts the same. We wait for fire, clear the screen, send to the player, and then we initialize the contents of the level, the enemies, the number of crystals we need to collect, things like that. Got to kick that watchdog again. This is the main loop here. So this is the main game loop. What we do first is we're going to read in from the joystick here. We'll see that code further down. And any key presses are going to be stored in D2. So we're looping just to slow the game down, and then we're going to process the D2 register and its movements. So once we've got any movements that have occurred, we're then going to redraw the screen. So we draw the user interface, the little bits of text in the corners, and then we clear the player object off the screen. Now, we've got various functions for drawing and clearing objects, and the objects in the game use a fixed format of 8 bytes per object, and they have an X position, a Y position, a sprite number, and also things relating to how the object moves and how it collides with other objects. So they're all held in an 8-byte format, and we'll see how that works later on. Now, the game works in acceleration, so if you press the up key, you'll start moving in the up direction and you'll keep moving until you stop. Because of that, if we accelerate too fast, we'll quickly lose control. What we do is we have a timeout, so if the player presses up, we'll start speeding up, but we won't keep processing that up press for a little while just because we don't want to accelerate too fast, and that's the timeout. If the timeout's non-zero, we're going to jump over the direction processing here. If we are processing directions, however, we're going to change the Y and X acceleration. Now, we loaded in from the joystick here, and that was stored in D2, and each bit in D2 is a different direction. And what we're doing here is we're testing all of those directions here, and we're changing the X and Y acceleration accordingly depending on which directions are pressed. If fire 1 is pressed, we're going to fire a bullet using the multi-platform code here. If fire 2 is pressed, we're actually stopping the acceleration. You've got a handbrake there, so we can stop. Now, if a direction was pressed, we've updated the key timeout, and we store that just here. Now, that's actually the end of the main loop. We've got the draw and move command here, which updates all of the graphics on the screen and handles all the movement of the objects. And then we're just looping back here. Now we're starting the graphics code. Here's the clear screen routine here. We're setting the auto ink here, and we are then going to just clear the entire fix map here. We just repeatedly write 0 bytes to the tile data. That will zero the entire fix map. What we've got here is the routines for printing characters. Now the font contains 96 characters, and there's no characters below ASCII 32. So what we're doing is we're subtracting 32, and then we are just calculating the screen position from the cursor X, cursor Y, which simulate a sort of drawing text cursor, so we can draw strings. We're using Show Sprite. Show Sprite really does all of our graphics. You can see it down here. We'll get to that in just a moment. When we want to remove an object from the screen, we're passing the object in A4. And first what we're doing is we're checking what collision program the object has. Collision program affects how the object interacts with the world, but a collision program above 250 is a dead object, or an object that's never been used. So we don't want to clear that off the screen because it's not actually on the screen. So if that's over 250, then we're returning. Otherwise, we're using the space symbol from our font to remove the object from the screen. And we're going to jump down to our sprite routines. Now what we're doing here is we're calculating the address in the fix layer of the tile or sprite we want to show, as it's called. Now we need to skip over the font, so we're adding 768 to the memory address of the tile we want to show. We're also adding the sprite frame, and we're having to shift that to the left 4 times to calculate the bank number of the tile, because as I say, there's 4 versions of each sprite for the 4 frames of animation. Sprite frame increments automatically for every iteration of the game, every tick of the game. It just rotates around between 0 and 3. Show Sprite will actually show the sprite to the screen, or the tile. I refer to them as sprites in the code, but they're actually fixed layer tiles. Now what we're doing here is we're showing a sprite that's been specified by an XY position and a number, but do get sprite object will get all of those settings from the object A4. It's written as AX there. That's a bug from the old Z80 version. So we're loading the sprite number, X and Y position from A4, and we're just multiplying those up to a tile position, and then we're going to show the tile to the screen. So we're calculating the address of our fix map, but we're also calculating the offset within the fixed layer ROM of the tile we want to show, and it's important that we include our ROM file YQuest6, and this was made with AccuSprite Editor, my sprite editor as always. And so we're including that at this memory address, and we need to make sure the memory address we include the file at matches the tile number just here. So this is going to show the tile number, and we've calculated the offset as needed here, and that will calculate the correct memory address of the tile we need to show. So we're doing that, and then we're transferring that into VRAM just here. We're just multiplying up the position, so we're calculating the tile position from the XY coordinates we were given, and we're showing that tile to the screen. When it comes to reading the joystick controls, we need to read in from the joystick hardware. Now I don't use the BIOS here, I'm reading directly in here. And I've got some code just to shift things around a bit to match the format of the other tutorials I've written here. But basically, we just need to read in from these addresses here, and that will get the joystick buttons for us. We're using those joystick buttons here with these wait for fire functions here. What we're doing here is we're waiting for the player to press the fire button and then release the fire button. This is used for the end of each level, and we're also re-randomizing the random number generator, but we need to remember to kick the watchdog, because if we don't, then during a loop like this, it would look like the game had crashed. And then finally we've got the palette here. This is in native format, and we've got a few definitions of common code that are used by the program. And that's really all there is to it. The rest of the code is multi-platform, and I've covered that before. If you take a look at my Z80 series, the code was basically the same. I did a lot of automatic conversions, so the variable names and the function names are identical. So that's all of the code for this version of the game. We're going to come back to the NeoGeo later on. We're going to have a version that uses hardware sprites and gets the graphics a little bit better. So if you like what you see today, please stick around and you will see that. I hope you've enjoyed this. I hope you've found it interesting. If you have, please like and subscribe. If you like the videos, YouTube recommends them to more people, and if you subscribe, I'm encouraged to keep making them. You can go to my website, you can download the source code and also the fixed layer ROMs and everything for today's example, so you can go ahead and use it. And as I always say, you're welcome to modify it and do whatever you want with it, and if you somehow manage to sell a program based on any of my code, you're welcome to do so. You don't need to give me credit. Anyway, I hope you've enjoyed this. Thanks for watching today, and goodbye.